say I have a wire that gets skinnier. We have a Kirchhoff rule, we have the voltage rule that we've talked about. There's a current rule also, or junction rule, that at any point current in equals current out. What's the definition of current? The math definition? What does I equal?
D over R.
More fundamental.
Q over G. or
Say it again?
DQ over DC.
All right. So we have dq in dt equals dq out dt. I can take each of these, and so dq in per unit length times dx dt. I guess this would be 1 equals dq out dx2 times dx2 dt. So basically, if this is region 1 and region 2, I've got this speed element right here. dq dx is just the cross-sectional area, and well, badly worded. So that would be dq dv times dv dx times dx dt equals the same thing over there. This charge per unit volume, that is our charge carrier density. dv dx is the cross-sectional area, dx dt is v. Looks very similar to something we had already. But notice that there's a relationship between the area and the speed. So as it gets skinnier, the current will pick up. Same with water. Ideally, same with traffic. Now, in reality, it doesn't happen with traffic, but imagine that you're about to lose a lane. If everyone started picking up speed, then you could just slide right into one of those open places. And the current and you would get no backup at all. But people tend to slow down. This is known as continuity. And one of the big principles here, one is that as area gets smaller, the current goes up. But this whole idea of the current into any point equals the current out of any point is rather critical for what we're about to do. Now there's one, but not really an exception, but there is one place that might seem like an exception right now of at any point in a circuit, current in equals the current out. What is a situation in which that does not seem to hold? Where you have charge flow into a particular point, but not the same charge flow out of that same point. Done experiments with them?
Series?
Series? Series of what?
Capacity.
If I have a parallel plate capacitor hooked up to a battery, I have current that's going to be flowing in onto this plate and then off of that plate. But I have a gap here. I have current flowing in onto the plate, but it doesn't look like I have any current flowing off the plate. There's a gap before it joins up again. And so that right there is something that gets resolved later on. That's Maxwell's contribution deals with that. Maxwell's contribution to Ampere's law deals with that. So for right now, we will just assume that it works. Now, let's actually do some analysis of a circuit, see how a capacitor and resistor combined in series will affect things. I'm going to take a simple RC circuit. And I want to figure out how things change with time. I'm going to start out with Kirchhoff's rule. I'm going to start here. I'm going to start working my way around. I know that the voltage, I gain potential going across the voltage. I'm going to lose it going across the resistor. And then that's going to be my positive plate, my negative plate of the capacitor. So when I go across it going to the right, I'm going to lose it. So I have a change in, actually I'm going to write it slightly differently. The change in voltage across the resistor, change in voltage, power supply, capacitor equals 0. Across the resistor, I have a formula. Delta V power supply is equal to minus IR minus, and what's the difference in potential across the capacitor?
0. Or, oh.
What is capacitance equal? They're believing in you, Sarah.
Q over the change in volts.
So Q over the change in potential or over the voltage. All right. So what is the voltage equal to? From this formula.
R over capacitance.
Now, I have, let's assume that R and C and my voltage of the battery are all common. First off, delta VPS is a nuisance to have to write every time, so I'm going to shorten that to epsilon, which represents the EMF. EMF is an ideal voltage. So if I have a 12-volt battery, the EMF we'll just assume is 12 volts. But when I actually, if I take that battery and I hook it up to a circuit, I'm not necessarily getting 12 volts out of it. Because the current, as the charges move out of and into the battery, they're going to bump into things. And so there's some internal resistance to a real battery. So EMF is just the ideal voltage. In reality, and the other, I don't think your textbook does this, the 152 textbook does it, where for batteries, they represent the battery as a resistor and some internal resistance. Sorry, as a power supply and some internal resistance. It's a nuisance to have to, these are small compared to any of the resistors probably you have in the diagram. So I tend to just ignore that and just assume a nice ideal. All right, so trivia here. For what does EMF currently stand? What does it represent?
Electromagnetic frequency.
No. I would say you were partially correct.
Electromagnetic field.
Not field.
Is the electromagnetic part right?
Yes and no. Go with electromagnetic. What else could F stand for?
Fluctuate.
Flux.
Not flux.
Force.
Yes. Originally, it was called electromagnetic force, and they put in they shortened it to EMF. At some point, they realized it's not a force; it's a voltage. It is not a force. Because it is not a force, calling it electromagnetic force, or sorry, electromotive. Wow. Sorry, electromotive force. Because it's not a force, it really shouldn't be called electromotive force anymore. So EMF currently stands for EMF. And it is pronounced EMF, it is not pronounced EMF. All right, so I have an epsilon there, just shorthanded. So I have epsilon is minus IR minus Q over C equals 0. Let's get rid of that stuff. So epsilon, R, and C are constants, so I have these two variables of current and charge. This is the charge that is on the plates. This is the current flowing across the resistor. Now, current that flows across the resistor ends up on the plate, so we're not having an issue here. We will in a moment. But I now need to express this in terms of a single variable if I want to actually solve it. And I know that current is dq dt. And so I'm now going to write this as epsilon minus, with a whole bunch of extra string marks, epsilon minus R dq dt minus Q over C equals 0. Let's get dq by itself, dq dt by itself. So I have dq dt is therefore equal to epsilon minus 1 over CQ. I have a first order differential equation. How do you solve it?
Where'd the
R go over R, there we go. Okay, thank you. How do you solve a first order differential equation? Pretty sure it's a Calc 1 thing. Maybe it's a Calc 2. Oh, guess
think there was a
it has to be Calc 2, there's an integral involved. Pardon?
there was a section of it, you just move, or you'll separate each variable with its respective, I'm
Yep.
messing up the words, but.
You're on the way there.
You put the Q with the Q.
Okay. Because I can't really separate this particularly easily, it's first order, I'm gonna bring that whole thing down and bring dt up. And I'm gonna do one other thing there. So I have dq over, I'm gonna leave the RC on this side. So I end up with epsilon C minus Q equals RC dt. That is taking too many shortcuts. Let's multiply through by, let's say, add R and C there, divided by, multiply everything by RC, I get RC dq dt is equal to epsilon C minus Q. Now I can take dq, okay, over epsilon C minus Q equals 1 over RC dt. That's looking better. Integrate. Epsilon, C, R are all constants. Those, so I don't have to, so it's some constant minus Q. Over here, I have 1 over RC that just comes all the way out. So this becomes 1 over RC times time, doing the limits of integration from 0 to t, here from 0 to q. That's a t there. How do we integrate this? Or I guess I'm asking, how do you integrate this? Come on, everyone's favorite technique.
U substitution.
Let u equal epsilon c minus q. du equals negative dq. So this becomes negative integral du over u from, let's see, so when q is 0, this is epsilon c, and then when it is q, this is epsilon c minus q. And that is equal to, as we found over there, 1 over RC times time. What is this?
Natural log of U.
So I've got I'm gonna bring the negative over to the other side also. So I have the natural log of u epsilon c to epsilon c minus q is equal to negative t over RC. Plugging stuff in, I get the natural log of epsilon c minus q over epsilon c equals negative t over RC. Let's get rid of that pesky natural log. So I have epsilon, well, actually, I have 1 minus q over epsilon c is equal to e to the negative t over RC. Doing the fancy math here, trying to isolate q. So I'm going to bring the q term over to the right and the exponential term over to the left. So I have 1 minus e to the negative t over RC is equal to q over epsilon c. And so q, as a function of time, equals epsilon c times 1 minus e to the negative t over RC. When time is 0, I end up with just epsilon c. Wow. This is the charge on the capacitor, so when time is 0, I end up with 1 minus 1, which is 0, so I end up with 0. I have no charge to start out with on the plate. Which makes sense, it's an empty plate to start with. The only resistance initially is coming from this resistor. But as soon as we can start getting charges on the plate, this is also going to provide some resistance. We're not going to come up with an R value, but it does affect the current flow. I now have Q as a function of T, so I can find my current, which is just the derivative of this with respect to time, which is epsilon C times 1 over RC e to the negative t over RC. My coefficients there, the c's cancel out, and I'm left with epsilon over r times e to the negative t over RC. And epsilon over r, that's a voltage divided by a resistance. When time is 0, this term becomes 1, and my current is this. This right here is just my initial current. It's as if the capacitor is not even there when I start out. So epsilon over R. So if this is my current versus time, it starts out at the peak value, but then the current drops off as the capacitor starts to fill. Give it enough time, current would be 0. Since we're dealing with an exponential decay, there's certain factors that are generally considered. There's a different tau, not the mean free time. This is the time constant for this RC circuit. And that's equal to RC. So if I know the capacitance and know the resistance, I can predict how long it would take for the current to slow down or to drop off. And so my current as a function of time is equal to epsilon over R e to the negative t over tau. Yeah, we got enough time. Questions? All right, so now let's drain the capacitor. I have a fully charged capacitor. I have a resistor